Hi everyone. I hope you can see me okay, and I hope you can hear me okay, especially. But for this semester, I did my research on the general theory of relativity and Einstein's field equations specifically. So for today, I'm going to be talking about what it is and just kind of the overarching definition. I'm going to be going over its applications that you see not only in the scientific field, but just touch on a few applications you may see in everyday life in the real world. And then I'm also going to be going over obviously the equation itself and then its components as well. So first of all, what is the general theory? So the general theory was first proposed by Einstein in 1915, and it stems from the special theory of relativity, as well as Newton's theory of universal gravity. Both of those were the basis of understanding of gravity, space, and time, but there were holes in both theories. Um, the special theory of relativity did not account for gravity, and so there's phenomena that could not be explained, and an example would be black holes. Both theories just had um, different little intricacies that wouldn't explain anything in whole. And it just left room for mistakes and just for not being able to explain things fully. Um, However, Einstein was able to connect gravity, space, time, mass, and energy with the general theory of relativity. Einstein discovered inconsistencies within the special theory because it did not account for inertia and weight. But by introducing gravity, it expanded what systems the theory could be applied to because it could be applied to arbitrary motion. There are many different mathematical concepts that make up the general theory of relativity, but one of the most important ones is Einstein's field equations. So, before we get into equations, I just want to talk about how the general theory of relativity affects us day to day. So, within the scientific field, it applies to basically all systems of space, including cosmology, black holes, and gravitational wave theory, among others. In our day-to-day life, however, things such as electromagnets, GPS navigation, and light are representative of the theory. So, relativity is responsible for the accuracies of a satellite being able to track speed, distance, and path while traveling. And that can be seen, or that's reflected in our GPS navigation. Being able to get the signal down to your phone in the time that it does is all because of relativity. And while I was looking into this, there was a nice quote that I found, and I felt like it explained relativity in a way that's not so confusing or scientific, I guess. And it was when you sit with a nice girl for 2 hours, you think it's only a minute. But when you sit on a hot stove for a minute, you think it's 2 hours. And that was said by Albert Einstein himself. And I just thought it was a really nice quote. All right, now let's start looking into Einstein's field equations. Again, though, before we look into the equations and its components, it is important to first understand what a tensor is. So a tensor is a concept that does not rely on a specific set of coordinates, and it can be applied universally. So in terms of the field equations, there are three symmetric tensors that are responsible for the 10 equations. So there's an equation for every one of the components in the matrix, and while there are 16 components, there are only 10 equations due to symmetry. So, for example, the component T01 is equal to T10 and so on. The indices that you will see for these tensors will always equal 1, 2, or 3. 0, 1, 2, or 3, sorry. So this is the Einstein's field equation. This is the basic equation representation of it. You can see that on the right here. And the first tensor of the field equations is the Einstein tensor, which can be seen on the left side of the equation. This is composed of the Ricci tensor and Ricci scalar. The Einstein tensor Tensor measures the curvature of space-time. So these are the first two tensors, symmetric tensors that are seen within the Einstein field equations. The Einstein tensor is described as a symmetric two tensor meaning that there are two indices. The next tensor is the energy momentum tensor. This can be seen to the far right of the Einstein field equation. The energy momentum tensor is also a symmetric two tensor and explains the universe's matter content while also encompassing the components of energy density, energy flux, shear stress, pressure, momentum flux, and momentum density. So if we go back one slide, you could see the tensor matrix on the left right here. Um, the components within this matrix is they each have they each explain a different component of the energy momentum tensor. So T double zero, seen in the top left of it, represents the energy density. T0, 1, 0, 2, and 0, 3 are representative of momentum density. T10, T20, and T30 represent energy flux. T11, T22, and T33 represent pressure. And T12, T13, T21, T23, T31, and T32 all represent shear stress. So, and then the last aspect of the field equations is the constant, which is composed of multiple constants, including the gravitational constant, g, and the speed of light, c. So this is an example of a condensed version of what the Einstein tensor looks like right now. It is composed of many second-order partials, and the summation of each term, both alpha and beta, will range from 0 to 3, resulting in each term having its own 16 terms. So what that means is if you take a look here, alpha can be seen up here, and as well as beta. So alpha and beta are at the top of each G term throughout every single term in here. Alpha can also be seen as a partial, and beta can also be seen at the end of each term. So within each of these terms, for example, this first term right here, alpha and beta will equal 0 in all spots here. And then when we move on to the next term, alpha will equal 0, beta will equal 1, alpha will equal 0, beta will equal 1. And that'll continue on throughout every single term. And so when this is all completely written out, each individual term, so here's one term, two terms, three terms, and so on, each term is going to have 16 of its own terms in order to um, encompass all the indices equaling 0, 1, 2, or 3. And that is all I have for you guys. I hope you enjoyed, and I look forward to watching everyone else's presentation. Thank you.